Welcome to this lecture on the different sources of delay encountered in Internet communication and the sample of delay mitigations. My name is Anna Brunström, professor in computer science at Karlstad University. As we have seen in earlier lectures in the course, latency is today a dominating factor for application performance. And many times it's a dominating factor that determines how we perceive the communication as an end user. One important aspect of latency as compared to other performance metrics such as throughput is that it is additive in nature and it accumulates over the communication session. This means that all the different sources of delay that we encounter adds up and leads to the final latency that we encounter. This is in contrast to throughput, where you, for instance, have the bottleneck that decides what throughput you will have in the communication. And if you increase the capacity of the bottleneck, you automatically also improve the throughput. This is not true for latency, as all the sources add up, and sometimes when you remove one source, this could lead to an increase in a different part of the network. So many sources, as I said, can contribute to latency, and in this lecture we will look in a bit more detail at some of them and also on the different mitigations. There are many different ways you can structure the sources of delay. In this lecture we will use the structure used in the survey that we published together with some of our colleagues a few years ago on reducing internet latency, techniques and their merits. And in this survey, we divide the different sources of delay into 5 main areas. Structural delays, which has to do with the structure of the communication path or the structure of the application. We have delays that are related to the interaction between the endpoints, delays, for instance, for setting up the communication and for recovering losses between endpoints. We also have delays that we encounter along the transmission path as our packet travels from the source to the destination. We look also at delays related to link capacities, both when you have a limited capacity, but also delays related to taking advantage of the capacity that is available. And finally, as the 5th main category for the sources of delay, the intra-end host delays, delays that we encounter within the end hosts. And we will follow the structure of this survey, and when we talk about the different delays, we will also see the connection to the different sections in the survey. So let us start by looking in a bit more detail on the structural delays. So here we have delays such as suboptimal routes or paths. So the delays here are related to the route that your packet takes from the source to the destination. So you typically go through many hops along the network, and this route may not always be very efficient or take a very short path. So for instance, if you communicate between 2 countries in Africa, due to peering agreements and the agreements between the ISPs, some of the packets may, for instance, go up to an internet exchange point in Europe. And this, of course, adds unnecessarily delay to the communication. Another form of structural delay is delays related to name resolution. Before you start to communicate, you often have to resolve the name of the communicating peer. And depending on how this is done, you may have more or less delay added to your communication. If you have the name cached locally, you can find it very quickly. Or if you have a DNS server located nearby, it may also be quick. But if you have to go far away and also maybe multiple hops to find the name, this will add delay to your communication. Structural delays also has to do with where we place content in the network. So if we have to go far away to reach our content, this of course adds delay. So here you have techniques such as caching that are frequently used to reduce delay, and this may be applied both for using network proxies and caches in the network, or also caching at the client side. Another method to reduce the delay due to the content placement is also to predict what content you will need and actually download it beforehand. The service architecture is a similar issue related to where you place your servers in the network. And also today, when we have a lot of virtualization, and our network functions are being virtualized where we place these virtualized network functions. If we co-locate them, that the functions that communicate with each other, we can reduce delays. We also see the trend in 5G networks with edge computing, where we now put a lot of the application logic at the edge close to the clients to reduce delay. So all these are examples of structural delays. So next we have the delays that we encounter as a result of the interaction between endpoints. Here we have, for instance, transport initialization delays. Before two peers want to communicate, you typically set up a connection between these peers, and this connection setup may encounter delays. Ways to reduce this is, for instance, to use parallel negotiation, something which is used in the happy eyeballs mechanism, where you can try and set up an IPv6 connection in parallel with an IPv4 connection. You also have mechanisms such as the TCP fast open, which reduces delay needed to set up a TCP connection. Here the idea is that if you have talked to the server before, you can use this knowledge to immediately send data in the connection setup. You also have techniques such as using application pipelining or persistent connections, something that is used in web traffic. So if you have a persistent connection, you don't have to open up a new connection for every web object. If you have a connection available, you can use an old connection for the new object. We also have secure session initialization. When you want to communicate, you typically not only want a connection, you want a secure connection. And getting this security can also add additional delay. Here, the new TLS 1.3 protocol is an example of how to reduce the delay for setting up the secure connection, cutting one of the round trips away as compared to TLS 1.2 when you set up a new secure connection. Of course, the new QUIC protocols combines transport initializations and the secure session initialization and allows you to do this in zero RTT if you have communicated with the server in the past. You also have delays that you encounter as a result of packet loss. This you can try and limit by having an application tolerant to loss so that you don't have to recover all lost packets, or you can try to reduce the packet loss detection time. And there has been several mechanisms introduced to TCP in the last few years to try to reduce this time. You may also use a mechanism called explicit congestion notification. So instead of dropping packets in the network when congestion occurs, you can send a marking on the packet and convey this information to the transport endpoints without having to drop the packet. We also have delays related to message aggregation. So typically TCP would like to try and aggregate a lot of data into a large packet before it transmits the data. If you have small packets to send, this may not be good, and you have there the Nagel algorithm that tries to reduce this delay. Next, we have the delays that we can encounter along the transmission paths. So when you send the packet from a sender to the receiver, there are several delays that you encounter along the way. You have the signal propagation delay, and this is something that you cannot completely limit, but still there are some ways to reduce it. You can try to have really straighter cable paths, or you can use a medium which has a higher signal velocity. So if you, for instance, use a microwave link, this has a quicker medium to communicate over, and it's also typically, of course, more straight than if you try to draw a cable between two communicating endpoints. But it may have some other problems in terms of the robustness, in terms of errors and so on. You also have the medium acquisition delays that you encounter when you try to access the communication medium. You have the serialization delays for sending your packets, and you may also encounter delays when you have errors on each of the hops on the link layer. And of course, you try to then recover them locally to not have to recover all the errors end to end. You also have delays in the switching and forwarding equipment along the path. And finally, you have the queuing delay, and this is a delay that we will look a bit closer at in this course. And the queuing delay is interesting because it can be quite large, and it's also highly varying depending on how much congestion you have in the network and what the different traffic sources look like. And there are a number of ways that you can try to reduce the queuing delay in terms of how you perform the scheduling and the queue management in the network. Next, we have the delays related to link capacities. This includes both delays that you encounter as an effect of insufficient capacity, and here, of course, you can try to increase this capacity by leveraging, for instance, multiple links. You may also get a shortage of capacity because you're sending a lot of redundant information. In web traffic, for instance, you try to reduce the information by using header compression, not sending the same type of header information redundantly over the network. You may also try to reduce the amount of information by using multicast if you are communicating the same information from a source to multiple destinations. Perhaps more interestingly is the delays that you encounter as a result of underutilized capacity. And this has to do with the delay that it takes to actually detect what capacity is available. So here you can try to have some more aggressive congestion control or more rapidly sensing the available capacity in the network. Of course, you have to be careful here because if you don't do this correctly, you may cause another type of delay, which is called collateral damage. And this is the delay that you encounter because other flows take up too much of the capacity. And some ways to try and avoid collateral damage is to use, for instance, low priority congestion control for flows that should not have a high priority in the network, and to try to tune your congestion control algorithms to also not overshoot their capacities. Finally, we have the delays related to the intra-end host delays, the delays that are internal to an end host. And here we have, for instance, delays due to transport protocol stack buffering. And we have seen a lot of optimizations going into the Linux kernel in the last few years to try and reduce this delay. You also have a delay called transport head of line blocking. And this is a delay that you encounter when packets arrive out of order. And if you need to provide an order delivery to the application, you have packets available, but you are not able to deliver them because some other piece of data is missing. And this is what we are called head of line blocking delay. You may also have various operating system delays. So we have seen that there are many different sources of delay, and there are also several different techniques you can employ to try and reduce these delays. So in the survey, we have also tried to look a bit at the gain versus pain of all these different techniques, or a subset of the techniques. And I'm not going through all of this here, but I want to show you a few key points in this evaluation. So what you see on the x-axis is the deployability of the different mechanisms, because some mechanisms are easier to deploy. They may be easier or less costly, and we call these more feasible, whereas other mechanisms are very hard or costly to deploy. So this is a distinction between the mechanisms. So if you have a mechanism that you can deploy, for instance, only at the sender, then that's fairly easily done. But if you need to have modifications in both the end hosts and in the network, things get more difficult. If you also have to do this all at the same time, things of course get even more difficult. And you can also have different gains from these different mechanisms. And in this first graph, we are looking at a scenario where we have a small 20 kilobyte flow communicating over a wide area connection. And for the baseline, we are assuming that you have an initial window of 3. And you can see in this graph also that the mechanisms are quite different. So if you, for instance, increase your initial window from 3 to 10, this will very consistently or predictably cut one round trip time from this communication. If you, on the other hand, employ an active queue management in your network to try and remove the queuing delay, the effect of this can vary greatly. If there is no congestion and no queuing, this will have no effect. On the other hand, if you have a very large delay in the queues and big buffers, then this queuing delay could dominate your performance, and eliminating this delay could give you a very substantial gain. And you can look at details for the paper for how these different mechanisms work. If we move on to look at the same graph but for a different communication scenario, I want to illustrate how the delay and the completion time for the flow is dependent on the size of the flow and the communication scenario. So here again we look at the 20 kilobyte flow, but this time over a local area network instead of a wide area network. And you see that the gains are similar. Over the local area network we have some smaller differences because the importance of the round trip time in relation to other sources of delay varies a little bit, but you see that the main behavior is very similar to the scenario with a 20 kilobyte flow over a wide area network. If we instead move to a third scenario, looking now at the large flow over a wide area network, we see that the behavior is very different. Now we see that most of the mechanisms for reducing latency that we considered in the gain versus pain analysis no longer has any noticeable effect. And this is because the initialization of the flow as well as the round trip time of a flow now has very little impact. When you need to transfer large flow over the network, the dominating performance is the data rate. So most of the optimizations that we looked at here, which try to speed up the initialization or reduce the round trip time, has very little effect. We only see two of the mechanisms that we considered having still a noticeable effect. The first one, the content delivery network, and this is due to the content delivery network moving the content closer to the user. This means that you typically also has a larger capacity available, and this will allow you a larger data rate. So the gain here comes from an expectation in an increase in the data rate and not from the reduction in the round trip time. And of course, if we can pre-fetch data, this will still give us a large gain in the completion time for the flow. So to conclude, we have seen that there are many sources that can contribute to the latency and then to the perceived application performance. The most critical source of delay varies over time, it varies across different communication scenarios, and it is dependent on the application traffic. This means that it is important to address as many sources of delay as possible. It's not sufficient to just remove one of the sources of delay and think that we have solved the problem. We have seen that there are many different techniques that can be applied to reduce latency. We have touched on them briefly in this lecture, and you can also refer to the survey paper for more details on many of these techniques.